Hello there, and a very warm, soft welcome to the sleepy scientist. Take a deep, calming breath, and let the gentle hush of this moment envelop you. Here, curiosity doesn't rush. It simply unfolds, like a quiet bloom in the moonlight. And science, well, science takes the most scenic, winding route to slumber, guiding us not just to knowledge, but to a profound sense of peace. Tonight, our gentle journey is all about one of the most mysterious, elusive forces we live by, yet barely grasp: time. Imagine it for a moment. Time. It's the silent river that carries us forward, moment by moment. It slips through our fingers like fine sand, shapes our days with an unseen hand, and occasionally, just for fun, plays the most delightful, confusing tricks on us. Especially when we're waiting for something as simple as a kettle to sing its boiling tune, or when that long-awaited package is just 5 minutes away. But before we gently unfurl the ticking tapestry of time, before we delve into its secrets and its soothing mysteries, I'd love to know, just in a whisper if you like, where in the vast, beautiful world are you listening from tonight? And what tranquil hour has arrived for you right now, in your own unique corner of the clock? It's quite fitting, isn't it? A soft, exploratory video about the very essence of time. And here we are, scattered across countless time zones, each of us arriving at this very moment, in our own, precious, unique slice of the clock face. Each tick, a personal whisper of the universe. If you find this quiet voyage soothing, if the gentle unraveling of scientific wonder brings you a sense of intrigue, or if it simply feels like a nice, soft way to unwind after the long, intricate dance of a day, I'd be ever so grateful. A gentle tap on the like button, perhaps, or a soft click to subscribe. It truly helps this little corner of calm, this quiet sanctuary, reach others who might also need a peaceful pause, a moment of gentle contemplation before they drift off. Now, I do hope that our exploration tonight isn't so utterly fascinating, so profoundly captivating, that it actually keeps you awake, your mind buzzing with newfound wonder. But if, by some delightful cosmic coincidence, it does, well then, at least you'll have learned something truly remarkable about the very fabric of the universe, about the nature of existence itself, before your thoughts finally slow, and you drift into the realm of dreams. So, let your shoulders relax, let your thoughts settle like dust motes in the quiet evening air. Ease into your most comfortable space, perhaps with a warm drink or beneath a favorite, soft blanket, and let's begin this peaceful journey together. Because somewhere, woven delicately between the fleeting seconds and the stretching centuries, between the wisps of our deepest dreams and the soft glow of the coming daylight, lies the endlessly unfolding, profoundly comforting story of time. A story ready to be gently whispered into the quiet of the night. Time has a truly curious way of stretching and shrinking, doesn't it? Like a warm, pliable piece of taffy pulled between our experiences. 10 minutes spent stuck in a slowly moving traffic jam, perhaps watching the raindrops trace lazy patterns on your windshield, can truly feel like an eternity, an endless, slow-motion crawl. Yet, those same 10 minutes, when you're completely lost in the joyous embrace of your favorite hobby, whether it's painting a delicate watercolor, solving a challenging puzzle, or simply listening to a beloved piece of music, they can disappear faster than the last coveted biscuit in the tin, leaving only crumbs and a lingering sense of delight. And yet, through all this, the clocks on our walls, the digital numbers on our phones, they tick forward with unwavering consistency, second after second, minute after minute. So, what on earth, or rather, what in our minds, is truly going on here? The answer, as it turns out, begins not with the grand, sweeping laws of physics, but with the intricate, wondrous workings of your own brain, our perception of time, that deeply personal, internal sense of when things begin, how long they endure, and when they gently come to an end is surprisingly, wonderfully flexible. Psychologists have a term for it, subjective time, and it's profoundly, deliciously influenced by a whole host of internal landscapes. Things like the focus of our attention, the swirling eddies of our emotions, and the rich, layered tapestry of our memories. In simpler, softer words, how you feel about time, how it plays out in the theater of your mind, can be vastly, beautifully different from how time is actually, objectively passing by. Let's begin our exploration with the familiar, sometimes exasperating, oddity of waiting. Imagine yourself, for a moment, in a doctor's waiting room. The walls are painted in a non-committal shade of beige, perhaps a shade that seems to absorb all joy. The magazines on the low table are ancient, their pages well thumbed, speaking of forgotten trends and faded news. And in the corner, a clock ticks loudly, its insistent rhythm a relentless, almost competitive sound, as if it's trying to win a global competition for the world's most annoying, attention-grabbing noise. 5 minutes spent in such a space can truly feel like half an hour, or even longer, a molasses slow drag. This is because your brain, starved for any genuine, engaging stimulation, turns its attention inward, like a searchlight sweeping the empty corners of a room, and that intense, internal focus makes you hyper-aware of each individual, languidly passing second, amplifying its presence. Now, compare that to the lively, flowing rhythm of a captivating conversation with a dear friend, where words and laughter intertwine effortlessly, or the absorbing quiet of getting utterly lost in the pages of a truly good book, where the world outside seems to melt away. In those cherished moments, you are fully, completely engaged. Your mind is dancing, weaving, exploring, and because of this profound absorption, your brain isn't keeping meticulous track of time so closely. It's almost as if your mind gives a gentle sigh of contentment and goes, "Oh, we're wonderfully busy here, deeply immersed. No need to watch the clock, no need to count the moments." And before you consciously realize it, hours have simply flown by, leaving only the pleasant echo of the experience. This beautiful state of profound absorption is sometimes called the flow state, a term elegantly coined by the renowned psychologist Mihaly Csikszentmihalyi. In this state, your conventional sense of time gracefully fades into the background, becoming a soft, indistinct hum, as you become utterly, completely absorbed in the vibrant, unfolding present. It's a feeling of timeless immersion, where the very act of doing is its own reward. Interestingly, the novelty of an experience also plays a subtly profound role in how we perceive time. When you encounter something truly new, something unfamiliar or surprising, your brain takes extra, meticulous time to process it, to absorb its details, and to store that rich information in the vast archives of your memory. Later, when you gently cast your mind back to that experience, it feels as though far more time must have passed than the clock might indicate, simply because there's a greater abundance of mental footage, more vivid, detailed recollections of the event. This is why, for many of us, childhood summers seem to stretch on forever, an endless succession of sun-drenched days. Your young brain was constantly encountering new experiences: the first taste of a wild berry, the first time you climbed a particular tree, the first secret whispered to a friend, and it logged every single, delightful bit of it, each moment a new, sparkling discovery. As we gently age, and our lives settle into comfortable, Familiar routines. Our brains become remarkably efficient at compressing memories. Almost like a skilled archivist. Fewer novel highlights. Shorter, more compact reels of memory, and consequently, time seems to speed up. A gentle, accelerated blur. Emotion, too, plays a deeply significant part in time's perceived elasticity. Studies have consistently shown that strong emotions, particularly fear and anxiety, can dramatically slow our perception of time, elongating moments of crisis into what feels like an eternity. Conversely, intense joy and excitement seem to speed it up, making thrilling moments feel fleeting. There's even a fascinating theory that in genuinely dangerous or intensely stressful situations, your brain doesn't just go into overdrive. It creates an exceptionally dense, richly detailed set of memories, capturing far more information per second than usual. This heightened recording density gives the powerful illusion that time has slowed down, creating a sort of vivid, almost dreamlike slow-motion playback effect when you recall the event. This is sometimes reported by people who've been in car accidents or other sudden, life-threatening emergencies. The sensation that the world unfolded in exquisite, agonizing detail. It's not that time actually slows down, but rather that your brain records so many more details per second, creating a richly textured, expanded internal experience. Then there's the curious, often uncomfortable case of boredom. You've probably heard the cheerful phrase, "Time flies when you're having fun," but it's equally profound, often unwelcome opposite, "Time crawls when you're bored," is just as true. Perhaps even more so. Neuroscientists have made intriguing discoveries, finding that when we're deeply, uncomfortably bored, the brain's internal pacemaker, and yes, that's a real, scientific term for a fascinating concept, becomes unusually more active. This increased activity, this energetic hum, creates more pulses in our perception, making time seem to drag, to stretch interminably. It's like having an overly enthusiastic, relentless drummer inside your head, tapping out every single, agonizing beat of a dull, uneventful moment, forcing you to acknowledge its slow, laborious passage. Even something as fundamental as our cultural background and the very language we speak can subtly, yet profoundly, influence how we perceive and conceptualize time. In English, we often talk about time as if it's a tangible, quantifiable resource. We spend time. We save time. We run out of it. Or we even invest it. This linguistic framing makes time feel like a commodity, a finite quantity to be managed. Yet, some languages, like Hopi, a Native American language, or certain indigenous cultures, don't treat time as a linear path you simply move along, but rather more like a vast, unfolding landscape or a dynamic set of ever-changing conditions. This fundamental difference in linguistic structure profoundly shapes how people in these different cultures think about the future and the past. In fact, in some parts of the world, people might point behind them to indicate the future, because it's unknown, unseen, and therefore behind their line of sight, and they might point in front of them to show the past, because it's already visible, already laid out before them. A reversal of how we typically picture things. It's a truly fascinating shift in perspective, reminding us that time is not just a universal tick, but a culturally shaped tapestry. But what about our inner clocks? Those mysterious, biological timekeepers that seem to operate beneath the surface of our conscious thought. Surely there must be some kind of consistent biological mechanism ticking away, giving us at least a rough, foundational idea of the passage of time, a steady anchor in the sea of subjective experience. There is, sort of, humans, along with almost all living organisms, possess something truly remarkable called a circadian rhythm *. This is a roughly 24-hour cycle that helps regulate a vast symphony of biological processes, our sleep-wake patterns, our core body temperature, the delicate balance of hormone levels, and even our digestive cycles. But that's more like a daily, deeply ingrained timer, a gentle, consistent beat, rather than a precise stopwatch for short intervals. For shorter periods, the fleeting seconds, the rolling minutes, scientists believe we employ a kind of mental timekeeper, often metaphorically compared to a discrete stopwatch nestled somewhere in the brain. This intricate system involves a complex network of brain regions, notably including the basal ganglia, crucial for motor control and learning, and the cerebellum, known for coordination and timing. It seems to rely on a steady, internal stream of neural pulses, like tiny, rhythmic electrical signals, when we try to estimate how long something has taken, or how long it might take. We are, in essence, subconsciously counting those internal pulses, interpreting their rhythm. That said, we're certainly not always good at it. Our time estimations can be wildly, delightfully off, especially when we're multitasking, our attention divided, distracted, our focus scattered, or emotionally charged, our internal landscape swirling. There's even a curious psychological phenomenon known as the asterisk return trip effect, asterisk, where the journey back from somewhere feels distinctly shorter than the trip there, even if the actual, objective amount of time taken is exactly the same. Why this delightful trick of the mind? On the way asterisk there asterisk, your brain is actively, busily processing new information, the unfamiliar landmarks, the subtle turns, the new sights and sounds. It's creating new memories, new mental footage. On the way asterisk back asterisk, however, it already knows the route. The novelty is gone, and the experience feels more familiar, more compressed. So, the brain has less new information to log, making the experience feel faster, more streamlined. And let's not forget, as we drift towards the softer edges of consciousness, the most universal, and perhaps most frustrating, distortion of time known to humankind, the snooze button. Somehow, those elusive, precious 9 minutes between alarms, that brief, hazy period of semi-slumber, feel profoundly, inexplicably shorter than any other 9 minutes in the entire universe. While there's no single, definitive hard science behind that asterisk specific asterisk feeling yet, it's probably another delightful, complex case of disrupted sleep cycles, incomplete consciousness, that dreamy, liminal state between waking and sleeping, and our wonderfully fuzzy internal stopwatch simply throwing up its hands in delightful, sleepy surrender, no longer bothering to keep precise track. So, as we gently reflect on what time asterisk is asterisk, at least as we personally experience it, it becomes beautifully clear. It's not merely a cold, hard number on a clock face or the silent, shifting shadow of a sundial number. It's so much more. It's a feeling, a deep, internal perception, a clever trick of memory, a dance of attention. It changes, beautifully and inconsistently, with our mood, our age, and even the very language we choose to speak. It speeds up, deliciously, when we're lost in love or absorbed in joy. It slows down, achingly, when we're gripped by fear or trapped in boredom. And sometimes, just sometimes, in those rare, precious moments of profound absorption or stillness, it seems to vanish altogether, leaving behind only the pure, unfiltered essence of the present. And while physics may eventually explain what time is on the grandest, most cosmic scales, our personal, wonderfully wobbly, and at times delightfully unreliable sense of time will always remain something deeply, intimately human, a soft, ever-shifting landscape within us, whispering secrets of subjective reality. If time itself remains an intricate, whispering mystery, then our relentless, beautiful efforts to measure it stand as a magnificent testament to both human ingenuity and, let's be honest, our endearing impatience. From the grand, ancient sundials that stretch towards the sun, to the breathtakingly precise atomic clocks that hum quietly in climate-controlled vaults, we, as a species, have spent countless millennia trying to wrangle this invisible, flowing force into something we can not only see and count, but ideally, perfectly schedule our lives around. Because while time, in its grand, indifferent wisdom, may indeed wait for no one, humans are profoundly, wonderfully fond of asking it to hold on just a minute. Let's begin our soft journey into the past, into the deep, echoing chambers of history, when the very first timekeepers weren't intricate clocks or neatly organized calendars, but the vast, celestial canvas of the sky above us. Our earliest ancestors were not just survivors. They were expert, patient observers of the heavens. The slow, majestic rising and setting of the sun, casting its golden light then drawing it away. The ethereal, ever-changing phases of the moon, waxing and waning in its silent dance. The subtle, yet profound, shifting of the seasons, like slow, deliberate tides across the land. These were nature's earliest, most reliable calendars. No batteries required, no complex mechanics needed. Just the steady, cyclical rhythm of the cosmos. The ancient Egyptians, a civilization of profound wisdom and meticulous organization, were among the first to formalize timekeeping with a touch of earthly ingenuity. Around 1500 BCE, they began to build towering obelisks, those monolithic stone pillars that pierce the sky. These weren't just monuments, they acted as gigantic, silent sundials. By patiently tracking the obelisk's long, shifting shadow as it crawled across marked lines on the ground, they could divide the daylight hours into segments. However, a fascinating quirk of these early devices was that the lengths of these segments changed with the seasons. An hour in the long, lazy days of summer was quite a bit longer than one in the crisp, shorter days of winter. It wasn't perfectly exact by our modern standards, but it was remarkably good enough for managing their agricultural cycles, scheduling their sacred prayers, and organizing their bustling society, which, even back then, was likely running just a little late for something, much like ours today. Water clocks, known as clepsydras, came next. A brilliant leap forward in consistency and utility. These ingenious devices, utilized by both the ancient Egyptians and later perfected by the Greeks and Chinese, measured time by the steady, rhythmic flow of water from one elaborately designed vessel to another. They were simple in principle, wonderfully consistent in their operation, and crucially, they could work just as effectively at night or on cloudy days. A monumental upgrade from the sun-dependent sundials. Some of these water clocks were surprisingly elaborate. Miniature marvels of engineering, complete with intricate gears that turned tiny figures, or even mechanisms that chimed the hours or rang gentle bells. You might softly say, they were the original smart devices, just delightfully wetter, and imbued with the quiet dignity of flowing water. Meanwhile, in the mystical lands of Mesoamerica, the Maya civilization, with their profound understanding of the cosmos, developed intricate calendar systems that tracked lunar and solar cycles with an astonishing, almost uncanny accuracy. Their long count calendar, a monumental feat of intellectual prowess, could measure spans of time covering thousands of years, anchoring their civilization to deep historical cycles and distant prophecies. For a civilization that, remarkably, didn't have metal tools for precision work or beasts of burden for heavy labor. Their grasp of the vastness of time and their ability to map its celestial rhythms was nothing short of cosmic. A testament to human intellect, gazing at the stars. But back in the gently evolving landscape of Europe, it wasn't until the Middle Ages that mechanical clocks began their slow, rhythmic tick into history. At first, these were grand, unwieldy contraptions, often installed high in the bell towers of churches and monasteries. They didn't yet have faces or hands as we know them today. Their purpose was simpler, yet profound. They just rang bells at regular, measured intervals, marking the passing hours, primarily to remind the monks when to pray, to break their fast, or to gather for contemplation. You might, with a gentle smile, suggest that monks were the world's first alarm clock users, albeit far more serene and contemplative about it than most of us are at 6 a. One of the first major leaps forward in mechanical timekeeping came in the 14th century, with the ingenious invention of the verge escapement. This was a truly clever bit of engineering, a pivotal mechanism that allowed for a far more controlled and regular release of energy, transforming the erratic motion of early clocks into a steady, rhythmic oscillation. This breakthrough made it possible to build smaller, more reliable, and crucially, more accurate mechanical clocks. Eventually, patient and skilled clockmakers began to add elegant dials and graceful hands to these mechanisms, so that people could actually see the time, not just hear its tolling, integrating time visually into the daily fabric of life. From there, the pace of innovation in timekeeping began to tick faster, each new invention building upon the last. By the 17th century, the magnificent pendulum clock entered the scene, a testament to the brilliant Dutch scientist Christian Huygens. Inspired by Galileo's earlier observations of pendulums, Huygens realized their potential for precise timekeeping. Pendulum clocks, with their steady, mesmerizing swing, were accurate to within a minute a day, a truly staggering improvement over earlier designs that could drift by hours, sometimes even more. If time was a wild, untamed horse, the pendulum was the sturdy, reliable saddle that allowed us to ride it with far greater confidence and control. The need for even more precise timekeeping became absolutely critical during the golden age of exploration and maritime travel. Sailors, venturing into vast, uncharted oceans, desperately needed to know their longitude, their precise east-west position, and that, in turn, required knowing the exact time at a fixed reference point, like the Royal Observatory in Greenwich, England. No matter how stormy the seas or how far from land they were. Enter John Harrison, an English carpenter of astonishing persistence and genius. He spent decades, a lifetime almost, inventing marine chronometers, ultra-precise clocks that could withstand the relentless rocking and rolling of a ship at sea, the drastic temperature changes, and the corrosive salt air. His fourth model, the legendary H4, was a triumph of engineering. It changed ocean navigation forever, transforming it from perilous guesswork into a science, and earned him a belated, but immensely well-deserved place in history, though it likely also elicited a few eye rolls from the old salts, who had been relying on stars and gut instinct until then. By the early 20th century, we gently stepped into the age of quartz. Quartz crystal oscillators, first developed with scientific precision in the 1920s, quietly revolutionized timekeeping once again. The magic of quartz lies in its remarkable property. When subjected to a precise electric current, a quartz crystal vibrates at an incredibly stable and consistent frequency. These vibrations, so uniform and reliable, were then used to keep time with far greater precision than anything mechanical could offer. Suddenly, clocks and watches could be manufactured cheaply, be easily portable, and be accurate enough to keep the trains running punctually, on time, or at least to give us absolutely no excuse when they didn't. But even the steady hum of quartz has its subtle limits, its tiny imperfections. If you truly want to know the most accurate time on Earth, the time against which all other clocks are measured, you'll have to ascend to the atomic level. Atomic clocks, first developed in the groundbreaking 1950s, measure time using the natural, incredibly precise vibrations of atoms, usually cesium or rubidium. A cesium atom, for instance, in its fundamental state, oscillates or tells time exactly 9,182,631,770 times per second. That seemingly impossibly large number isn't just a piece of scientific trivia. It's the official, internationally agreed upon definition of a second, according to the International System of Units (SI). These clocks are so unimaginably precise that if you run one continuously for 100 million years, it would be off by less than a single second, which is truly grand, assuming you have 100 million years to patiently wait for your tea to steep to perfection. Today, atomic clocks are not just scientific curiosities. They are the silent, indispensable architects of our modern, interconnected world. They are used to synchronize everything from the intricate networks of GPS satellites that guide our phones, to the vast, global internet servers that power our communication, to the complex systems of telecommunications, and the lightning-fast operations of global financial markets. Without them, your phone's map application wouldn't know where you are with any useful accuracy. Your bank transactions would descend into bewildering chaos, and half the world would mysteriously miss their crucial Zoom calls, unable to coordinate. Time, once humbly measured by the slow, gentle drip of water or the shifting shadows of the sun, now depends on atoms delicately flipping between energy states, like microscopic metronomes humming quietly in high-tech, climate-controlled vaults, deep underground or in orbiting satellites high above. And yet, despite all this astonishing precision, despite our mastery of measuring its fleeting passage, time still feels strangely, wonderfully personal. We can meticulously divide it into hours, minutes, and seconds. We can watch it scroll by, a relentless stream of glowing numbers on digital screens. But no matter how finely we slice it, how precisely we attempt to capture it, we each live it profoundly, uniquely differently. So, why did we begin this arduous, beautiful quest to measure time in the first place? Some historians and scientists suggest it was to regulate the rhythm of prayer in ancient monasteries, aligning human devotion with cosmic order. Others believe it was primarily to grow crops more effectively, marking the precise passage of seasons for planting and harvest, a matter of survival. Still others point to the need to mark seasons for migration or to schedule complex trade routes across vast distances. But maybe, just maybe, it's because humans, for all our love of grand stories and the silent, shimmering stars, are deeply, fundamentally comforted by rhythm, the steady, predictable beat of time, no matter how elusive its deeper nature, gives shape to our days, offers a profound sense of order in our often chaotic world. A gentle tick, a soft talk, a tiny, reassuring whisper from the universe saying, "You're here, now. This moment is yours." And that, after all, is what time has always been for us. Not just a cold, abstract measurement, but a warm, constant, deeply comforting companion. For most of human history, as we gently explored, time was very much a local, personal affair. It rose with the golden light of the sun, casting its long shadows, and gently ended with the quiet appearance of the stars, ushering in the deep velvet of night. It ambled through the hours at the mercy of the village bells, the cheerful bird song greeting the dawn, or the enthusiastic, unignorable call of a rooster. But then, into this rather charming, localized understanding of time, stepped Isaac Newton. He was not merely content to describe the world. He possessed an insatiable, brilliant drive to pin it down, to articulate its fundamental laws with crystalline clarity. And that ambition, naturally, included the very essence of time itself. Newton, the towering 17th century English physicist, mathematician, and even alchemist, with his famously dramatic, flowing hair and a knack for profound, often Apple-related anecdotes, gave the world a model of the universe that would profoundly dominate scientific thought for over 2 centuries. In his powerful, elegant view, space and time were not fluid, subjective experiences. They were like a grand, immense, invisible stage, stretching infinitely, upon which the magnificent drama of the universe precisely unfolded. The actors on this stage, the majestic planets in their orbits, the humble apples falling from trees, the cannonballs arcing across battlefields, and eventually, the delightful, wobbly motion of bicycles moved about with predictable grace. But the stage itself, this fundamental backdrop of space and time, never changed. It was absolute, immutable, a constant, unwavering presence. Time, in this revolutionary picture, was absolute. It ticked along at a constant, unvarying rate, flowing identically everywhere for everyone, forever. It was a universal metronome, beating out the rhythm of the cosmos without deviation. This concept, absolute time, was utterly central to Newton's groundbreaking physics. In his own meticulous, profound words, penned in the Principia Mathematica, he stated, absolute, true, and mathematical time, of itself, and from its own nature, flows equably without regard to anything external. Let's gently unpack that for a moment. In other words, Newton posited that time is like an immense, silent river, a perfect, unhurried current that flows at a steady, unchanging pace, utterly regardless of whether anyone is watching its flow, counting its moments, or simply floating along its serene surface in a small, contemplative canoe. It existed independently, utterly unaffected by the events transpiring within it. This idea of an absolute, unchanging time made intuitive, comforting sense to many. If you were to drop an object today or tomorrow, here on this quiet floor or in a bustling city, half a world away, Newton's elegant equations could, in theory, tell you exactly where it would be at any given point in time. Assuming you had enough common coffee, a solid grasp of calculus, and a very precise initial measurement. Time was not a variable. It was the steady, unwavering backdrop against which all motion, all force, and all gravity did their predictable, majestic thing. Newton's absolute time gifted scientists with an incredibly powerful, versatile tool. It allowed them to describe motion in exquisitely precise terms, to synchronize events across vast distances with a common temporal reference, and to create remarkably reliable predictions about the behavior of physical systems. If you desired to calculate the intricate orbit of a distant planet, the rhythmic swing of a pendulum, or the arc and fall of a cannonball, you could now plug it all into one neat, coherent mathematical framework. Time in this model was truly universal, the same everywhere for everything, ticking along in perfect, impartial harmony, a cosmic clock orchestrating the universe. But for all its immense usefulness and profound predictive power, this beautifully absolute idea came with a rather large, unspoken assumption that time was a thing in itself, a distinct entity, existing entirely independently of the stuff and events happening within it. A kind of invisible, omnipresent metronome keeping the precise, unvarying beat of the cosmos, whether anything was actually occurring or not. There were, however, a few gentle but firm dissenting voices, notably that of the brilliant philosopher and mathematician Gottfried Wilhelm Leibniz. Leibniz, Newton's intellectual rival, and, somewhat amusingly, a co-inventor of calculus, leading to one of history's great scientific priority disputes, simply didn't buy into the idea of absolute time, or for that matter, Newton's specific version of calculus. Leibniz argued, with elegant precision, that time was not some universal, pre-existing backdrop, but rather a profound measure of change, a sophisticated way of describing the sequential order of events. Without events, he claimed, there is no time. It's not a thing on its own, he posited, but a fundamental relationship between things, a description of their succession. Imagine, for a soft moment, a clock ticking away in a universe that is otherwise completely empty, devoid of any matter, energy, or events, ticking in total silence and absolute darkness. For Newton, that clock is still diligently measuring time, its absolute flow unaffected. For Leibniz, however, it's just a beautifully crafted, but ultimately meaningless, fancy paperweight, with no one to notice its ticks, no events to mark. To him, time only truly has meaning, only truly comes into being, when things happen, when changes occur. Newton, however, wasn't having it. He insisted, with his characteristic intellectual force, that time was intrinsically real and flowed regardless of what was going on. Which, to be fair, does perfectly match the feeling of waiting for a pot to boil. The pot is inert, but time feels very much present and moving. Newton's ideas eventually became the unshakable foundation of what's now universally called classical mechanics. And for a very, very long time, hundreds of years, in fact, classical mechanics worked beautifully, elegantly, and with astonishing predictive power. It could describe, with breathtaking accuracy, the motion of falling objects, the rhythmic swing of pendulums, the majestic orbits of the moon and planets, and even, with enough dedicated effort and intricate calculation, the delightful, complex motion of a juggling unicyclist. So, it's truly worth pausing for a quiet moment to admire just how profoundly successful Newton's framework was. For centuries, scientists across the globe relied on his concepts of absolute time and space to explore, understand, and predict the natural world. Clocks became ever more precise, enabling more accurate measurements. Navigation improved dramatically, guiding ships across oceans. Engineering leapt forward with new principles. Steam trains, those magnificent symbols of progress, ran reliably on time. Or at least had a much better, scientifically backed excuse when they didn't. But here's the gentle, inevitable twist in the grand cosmic story. As wonderfully good as Newton's model was, it eventually began to show subtle cracks under new, unexpected pressures, particularly as scientists delved deeper into the mysteries of light and electromagnetism. In the 19th century, experiments, particularly those by Michelson and Morley, noticed something truly strange and profoundly counterintuitive. The speed of light in a vacuum appeared to be always the same, a universal constant. No matter how fast you, the observer, were moving. That simply didn't make intuitive sense in Newton's universe. If you were driving a car and sped up, you should, logically, catch up to a beam of light a little more quickly, or at least perceive it differently, right? But it didn't. The light always sped away at the exact same, unvarying pace, seemingly indifferent to your motion. This perplexing problem simmered, a quiet but persistent anomaly, for a while. A fascinating puzzle without a clear solution. Until, that is, a young, unassuming patent clerk in Bern, Switzerland, by the name of Albert Einstein, entered the scene. But we'll gently leave his transformative entrance for another, equally profound chapter. A later moment in our story of time. Suffice it to say, he would take Newton's absolute time, give it a respectful, polite nod, acknowledge its profound historical significance, and then, with breathtaking elegance and revolutionary insight, turn it completely upside down, revealing a deeper, more fluid reality. Still, Newton's powerful idea of time as an ever-flowing, universal quantity left an incredibly deep and lasting imprint on both science and our everyday culture. We still instinctively speak of time as something we can waste, spend, or save. All phrases that make perfect, intuitive sense if time is indeed a precious commodity, a resource trickling away. Our structured workdays, the insistent ring of school bells, the precisely timed settings on our microwave ovens, all, in their essence, run on the comforting, unspoken belief that time ticks the same for everyone, everywhere, and in many, indeed most, everyday situations. That belief is still perfectly, practically true. When you're gently baking a cake, rushing to catch a bus, or trying to remember the precise moment your online order is due to arrive. Newton's time works just fine. It's only when we start dealing with phenomena at incredibly high speeds, in the presence of unimaginably strong gravitational fields, or at the bafflingly tiny scales of the quantum realm, that Newton's beautifully clear picture begins to subtly, tantalizingly blur. So, in the grand, unfolding story of time, Isaac Newton, with his profound genius, gave us a solid, foundational middle chapter. He painted a magnificent vision of a predictable, mechanical universe, running like exquisitely tuned clockwork, its gears meshing in perfect harmony. He brought order to the vast, often bewildering cosmos, and made time something we could measure, something we could trust. And, if only for a glorious, brief historical period, something we believed we could truly understand. But time, as we'll see, has more than one remarkable personality, more than one hidden dimension. And while Newton's absolute time is wonderfully logical and comforting in its simplicity, the universe itself, in its deepest, most wondrous complexities, may not be quite so straightforward after all. If Isaac Newton, in his profound wisdom, imagined time as an endless, serene river, flowing at a steady, unchanging pace for everyone, everywhere, then Albert Einstein, with a twinkle in his eye and a revolutionary gleam in his mind, came along and, with quiet confidence, suggested, actually, it's more like a wibbly-wobbly trampoline. Now, that's certainly not a direct quote from his esteemed papers, but it's a delightfully vivid analogy that captures the essence of his groundbreaking insight with surprising accuracy. In the early years of the 20th century, a period of immense scientific ferment, Einstein, then just a young man of 26, working diligently at the Swiss Patent Office, and quite possibly spending his lunch breaks or late evenings rewriting the very universe in his mind. Quietly, profoundly, appended our entire understanding of time. His revolutionary ideas, so radical they initially baffled many of his contemporaries, didn't just add to our knowledge, they reshaped the very fabric of reality as we had conceived it. He called his grand framework relativity, and it unveiled itself into parts. First, special relativity in 1905, and a decade later, the even more encompassing general relativity in 1915. Both of these theories, in their own elegant ways, had plenty of deeply surprising, non-intuitive things to say about time. Let's gently ease into special relativity. The first of his intellectual tremors, one of the cornerstone ideas of special relativity, is elegantly simple, yet profoundly consequential. The laws of physics, including the immutable speed of light, are the same for all observers, no matter how fast they're moving or in what direction. This seemingly innocuous principle immediately causes a profound problem for Newton's absolute, unwavering time. In Newton's classical world, if two people are moving at vastly different speeds, say, one standing still on Earth, the other hurtling through space in a rocket, they would still agree on when things happen, on the precise simultaneity of events. But in Einstein's new, astonishing world, that's simply not necessarily true. Events that appear perfectly simultaneous to one person, nestled in their own frame of reference, might not look simultaneous to someone moving at a significantly different speed. The very concept of now becomes relative. This mind-bending shift leads directly to one of the strangest, most captivating consequences of special relativity: time dilation. Simply put, the faster you move through space, the slower time passes for you, relative to someone who is standing still or moving at a significantly slower speed. Imagine, for a moment, that you were to board a sleek, advanced spaceship, and zoom off into the cosmos at near light speed, perhaps on a grand tour of distant nebulae. Your onboard clock, designed for perfect accuracy, would tick subtly, yet demonstrably slower than the one left behind on Earth. You would age more slowly. Your hair might take longer to grow, and you'd tragically miss entire seasons of your favorite streaming shows back home, returning to a world where decades had passed for your loved ones, while you had experienced only a few years. This isn't merely the stuff of exciting science fiction narratives. It's a firmly established, experimentally observed fact. One of the most famous, elegant experiments involved flying incredibly precise atomic clocks, the same kind we discussed earlier around the world on high-speed airplanes. When these airborne clocks were later compared to identical atomic clocks that had remained stationary on the ground, the airborne ones had, indeed, ticked ever so slightly more slowly, by mere nanoseconds, not enough for you to notice in your everyday life. Certainly, unless you're extraordinarily punctual, but undeniably enough to prove, beyond a shadow of a doubt, that time truly does slow down with speed. And then, there's the delightfully perplexing twin paradox. Imagine two identical twins, born at the same moment, sharing the same initial timeline. One twin, the adventurous explorer, boards a futuristic spaceship, and flies around a distant galaxy at incredibly high speed, experiencing the relativistic effects of time dilation. The other twin, the patient homebody, stays back on Earth, dutifully feeding the cat, tending the garden, and waiting. When the traveling twin eventually returns, having experienced only a few years subjectively, they will be visibly, undeniably younger than their sibling, who has aged significantly more. The paradox isn't a true contradiction in physics. It's a fascinating, counterintuitive feature of relativity, a confusing, mind-bending, yet entirely real one. But speed, as it turns out, isn't the only cosmic phenomenon that subtly, yet powerfully, messes with time. In 1915, a decade after his initial breakthrough, Einstein expanded his revolutionary theory into something even grander, more encompassing: general relativity. This profound theory dealt with the enigmatic force of gravity, and in doing so, it revealed that gravity, too, could elegantly, profoundly warp time itself. General relativity describes gravity not as a mysterious, invisible force pulling objects together, as Newton had conceived, but as the elegant curvature of spacetime caused by the presence of mass and energy. Imagine space and time not as a rigid, unchanging stage, but as that soft, elastic trampoline. The more massive an object, be it a star, a planet, or even, humorously, your friend's notoriously overpacked suitcase, the more it creates a dent, or a bend, in this spacetime fabric around it. If time were painted onto that elastic mattress, flowing along its surface, it would stretch and warp right along with the space, slowing down where the dent is deepest. What this profound insight means is that time runs more slowly in stronger gravitational fields. If you were to stand very close to something truly massive, like the swirling event horizon of a black hole, or perhaps, in a more earthly example, at the very base of a towering mountain, time would tick subtly, yet measurably, more slowly for you than for someone farther away from that massive object, perhaps at the mountain's peak. Again, this isn't just a theoretical abstraction from a chalkboard. It's a real, measurable effect, precisely observed even here on Earth. In one elegant experiment, two super-precise atomic clocks were placed at slightly different altitudes, one at the base of a mountain and one at its very top. The clock lower down, closer to Earth's stronger center of gravity, was indeed observed to tick a tiny bit more slowly than the one higher up. Even a height difference of just a few centimeters can cause a measurable, albeit minuscule, change in the passage of time. So yes, technically speaking, your head is aging ever so slightly faster than your feet. A curious, gentle irony of gravity. This fascinating phenomenon, often called gravitational time dilation, has very tangible, real-world consequences that affect our daily lives, often without our conscious awareness. The GPS satellites orbiting Earth, which tirelessly guide our navigation systems, experience both types of time warping. They are moving incredibly fast, at speeds of roughly 14,000 kilometers per hour, which, according to special relativity, causes their onboard clocks to tick slightly slower. But they are also much farther from Earth's strong gravitational pull than we're on the surface, which, according to general relativity, causes their clocks to tick slightly faster. To ensure your phone's map remains accurate to within meters, their onboard atomic clocks are constantly, precisely adjusted to account for these delicate, dual distortions. Without those meticulous corrections, your precise location would be off by several kilometers within mere minutes, leading to very confused navigators and many missed turns. Time, it seems, doesn't just pass, it wobbles and bends, and our sophisticated technology has to wobble and bend right along with it. So, what does all this profound, mind-bending insight mean for our fundamental understanding of time? Einstein, with his unparalleled genius, showed us that time isn't Newton's absolute, universal river, flowing identically for all. Instead, it's more like a stretchy, dynamic fabric, intricately woven together with space itself, forming a unified entity called spacetime. This spacetime fabric can expand, contract, bend, and twist, gracefully responding to the presence of mass and energy, to the very dance of the universe. And that, in turn, means your time, the precise pace at which you personally experience the universe, depends intimately on where you are in a gravitational field and how fast you happen to be moving through space. It's a deeply strange, profoundly counterintuitive idea, to be sure, but also kind of beautifully, poetically profound. Time is no longer the same for everyone, everywhere. It's personal. It's relational. It's a bit like your unique taste in tea, or your favorite kind of quiet moment. Einstein's groundbreaking work didn't just rewrite physics textbooks. It changed how we fundamentally see and interpret reality itself. Time is not a fixed, rigid background against which events merely play out. Number. It's an active, participating part of the cosmic dance, subtly shifting with the rhythm of matter and motion, shaping and being shaped. And even though most of us don't consciously feel time stretching or shrinking in our comfortable, everyday lives, every single second we live, every breath we take, is subtly, invisibly shaped by these profound, delicate distortions of space-time. So, next time someone gently, perhaps even exasperatedly, tells you they're running out of time, you can offer them a soft, knowing smile and, with a quiet, comforting voice, gently remind them, actually, time is running out differently for you, darling. Depending on your velocity through space and your proximity to any significant gravitational mass, it's all relative. You see. Then, perhaps, pause, offer a warm cup of tea, and maybe, just maybe, gently duck, as their mind tries to untangle that delightfully complex thought. The universe, it whispers, is far more intricate and wonderful than we often imagine. Let's imagine, just for a moment, as you drift deeper into a gentle, contemplative state, that you wake up one quiet morning and find everything running perfectly, impossibly backwards. Your crispy, buttered toast leaps gracefully out of your mouth and lands, perfectly reassembled and pristine, back onto a waiting plate. Your steaming cup of tea, with its soothing aroma, grows mysteriously hotter as you drink it, the ripples on its surface pulling inward. Raindrops, shimmering like tiny jewels, fly upward from the glistening pavement into the grey sky, rejoining the clouds. Strange, undoubtedly, impossible. According to the most fundamental, elegant laws of physics, perhaps not exactly, or at least, not strictly forbiddance. This odd, intriguing little thought experiment leads us gently to one of the most profound, yet often perplexing questions in science. Why does time seem to have a direction? Why is it a one-way street, always moving from yesterday to tomorrow, never the other way around? In most of the fundamental laws of physics, from the majestic, elegant equations of Newton's laws of motion, to the strange, quantum mechanical descriptions of subatomic particles, time doesn't truly have a preferred direction. These equations are, in a very deep sense, time-symmetric. They work just as beautifully and consistently backwards as they do forwards. If you were to meticulously film to tiny particles colliding, and then play that film in reverse, the physics would still perfectly check out. No alarms would go off in the universe's underlying equations. No fundamental rule would be violated. The reverse motion would look just as physically plausible as the forward motion, if we only considered the basic interactions. And yet, in our everyday lives, in the soft, tangible world we inhabit, time feels unequivocally like a one-way street, an irreversible current. Eggs, once cracked and scrambled, do not magically unscramble themselves and leap back into their pristine shells. A carefully written letter, once burned to ashes, does not reassemble itself into legible words and crisp paper. We remember the past, those indelible moments etched into our minds, but we can never, ever remember the future, that unfolding mystery. So why this profound, experiential disconnect. Why does time, at our human, palpable scale, march relentlessly, unyieldingly, from the comfort of yesterday to the uncertainty of tomorrow? Enter the elegant, powerful concept of the arrow of time. The arrow of time is a beautiful, vivid metaphor used to describe the singular, one-way direction in which time appears to flow, irrevocably from the past to the future. And the deepest, most fundamental key to understanding this arrow lies in one of the most important, and occasionally delightfully untidy, laws of physics. The second law of thermodynamics. This law, in its essence, tells us something profoundly simple yet deeply consequential. That in any closed system, a system that doesn't exchange matter or energy with its surroundings, like, hypothetically, the entire universe itself, entropy always increases over time. Entropy, a term that sounds complex but can be gently understood, is a fundamental measure of disorder or randomness, of the number of possible arrangements of particles. In simpler, more comforting words, things tend to go from tidy to messy, from ordered to chaotic, from organized to jumbled. Think of it this way, gently, you can easily scramble an egg, transforming its ordered yolk and white into a chaotic, delicious mess. But you cannot, by any natural process, unscramble it and return it to its original, perfectly separated state. Your neatly organized desk, a beacon of initial order, will naturally, inevitably become cluttered with papers, pens, and forgotten coffee mugs, unless you actively, consciously intervene to organize it. Socks, those mysterious, whimsical items, will always, inevitably disappear mysteriously into the laundry vortex, leaving behind lonely, unmatched pairs. But they never, ever spontaneously reappear in perfect, pre-matched sets. This pervasive, relentless tendency toward increasing entropy, toward greater disorder, is what fundamentally gives time its intrinsic, undeniable arrow. It's why we experience events in a particular, irreversible sequence. The low entropy past, with its specific, ordered arrangements, gracefully, inevitably becomes the high entropy future, with its expanded, more probable, and more disordered arrangements. And there's simply no reversing this cosmic flow, no turning back the hands of the clock of disorder, unless, of course, you happen to be a time traveler from a sci-fi novel, or a fictional wizard with a very specific, entropy-defying spell. Consider this vivid image. Imagine a delicate glass, slipping from your grasp, and shattering into a myriad of tiny fragments across the floor. That scattered state is a high-entropy state. The shards are spread out. Kinetic energy has been dissipated into heat and sound, and the information about its previous ordered structure is dispersed. It is an exquisitely, astronomically unlikely event that all those tiny fragments would spontaneously, by random chance, leap back together, perfectly reassembling themselves into a pristine, whole glass. Not strictly impossible according to quantum mechanics, where anything with a non-zero probability can, in theory, happen, but so astronomically improbable that it effectively is impossible on any human timescale. And that, in essence, is the key. The fundamental laws of physics allow for time reversal in theory, but the overwhelming, statistical nature of probability stands firmly, immovably in the way of such large-scale reversals. This profound realization leads us to one of the most intriguing, and perhaps slightly unsettling, questions in the realm of cosmology. Why was the universe in such an extraordinarily low entropy state to begin with? After all, if entropy must, by its very nature, always increase. Then there had to be an initial starting point, a kind of cosmic neat and tidy drawer, from which all this magnificent, ever-increasing disorder could gracefully unfold. The leading, prevailing theory, whispered among cosmologists, is that the early universe, just moments after the thunderous, fiery Big Bang, was incredibly uniform, astonishingly smooth, exceptionally ordered, a state of remarkably low entropy. Over billions of years, the relentless forces of gravity and cosmic expansion did their majestic, transformative thing, and the universe gradually got clumpier, more structured in some places, like galaxies and stars, and paradoxically, more chaotic overall as energy spreads out. Galaxies formed, stars exploded in supernova grandeur, and, of course, socks continue to disappear into the accelerating, entropic rate of our laundry. But why it started that way, why the cosmic drawer was initially so neatly organized, remains one of physics's biggest, most tantalizing open mysteries. Some scientists, in their deep contemplation, suspect the answer lies in the profound, intricate relationship between entropy, the flow of time, and the very geometry of space itself. Others wonder if the question is even truly meaningful from a deeper, fundamental perspective, or if we're simply asking it from the wrong angle, like a curious goldfish trying desperately, yet futilely, to understand the encompassing nature of water. There are, wonderfully, other arrows of time too, each subtly yet consistently pointing the same, unidirectional way, reinforcing the cosmic flow. There's the psychological arrow. We remember the past, those vivid, personal echoes, but we never remember the future. That's because memories require physical processes in the brain, the creation of neural connections and chemical changes that leave behind tangible traces. And those traces, the very act of their formation, are part of the universe's overall entropy increasing. You can't remember the future because it simply hasn't happened yet. And thus no physical traces, no neural pathways, have been laid down for your brain to recall. Then there's the causal arrow. Causes consistently, invariably precede effects. You flip a light switch, and then, and only then, the light comes on. You don't witness a light turning on and then decide to flip the switch unless you're a very peculiar observer indeed. Again, this follows the inexorable march of entropy. Flipping the switch adds energy to the system. The light spreads out as photons, and the universe becomes a slightly, irrevocably messier, more disordered place as that energy disperses. And finally, there's the cosmological arrow. The ongoing, majestic expansion of the universe itself. The fact that galaxies are moving away from each other. Space is continually stretching and thinning, and everything is gradually cooling down over cosmic time. All contributes to a powerful, overriding sense of direction to the cosmos. If, purely hypothetically, the universe were to someday begin contracting, to pull itself back inward in a big crunch, would time then feel like it were running backward for hypothetical observers? That's a theoretical playground scientists still gently enjoy exploring. A profound thought experiment that keeps the cosmic imagination alive. It's worth noting, though, that these various arrows, the thermodynamic arrow of entropy, the psychological arrow of memory, the causal arrow of events, and the cosmological arrow of expansion all line up, remarkably. They all point, in concert, in the same consistent direction, from past to future. Which is comforting in a way, isn't it? It suggests that time isn't just a random illusion, a whimsical trick of our minds, but something deeply, fundamentally woven into the very structure of reality itself. a profound direction carved by the ceaseless flow of energy. The relentless, inevitable march of disorder, and the gentle, ever-spreading unfolding of everything from a once very tidy, ordered beginning. But not everyone is entirely convinced that time, as we experience it, is truly fundamental. Some thoughtful physicists argue that the arrow of time is an emergent phenomenon, something that arises only when complex systems, like our conscious minds, observe simpler ones, like a cup of tea gently cooling or an egg beautifully scrambling. In some profound interpretations of quantum mechanics, time is seen as just another parameter, a label for different states of the universe, not a force, not a flowing river, just a descriptive coordinate. The universe, in its raw, quantum essence, doesn't feel time. We do. And that, perhaps, is the curious, most human thing of all. No matter how deeply we dig into the intricacies of entropy, the vastness of probability, or the elegance of equations, time continues to be both incredibly real in its effects and maddeningly elusive in its fundamental nature. It's something we ride like a gentle current, a universal river. But we can never quite step outside of it, to observe it truly from a detached perspective. We don't know what's ahead in its unfolding flow. We can't go back to edit its past. And yet, we live our lives by its comforting, unwavering rhythm, comforted by the profound, quiet fact that the future, however uncertain, is always on its way, bringing new possibilities. So, the next time you feel, perhaps with a soft sigh, that time is slipping gently away from you, remember it's not truly lost. It's just following the one rule it's really, profoundly good at. Moving forward, steadily increasing entropy, and leaving a whimsical, often charming, trail of mismatched socks and empty teacups behind. Little cosmic breadcrumbs of change and beautiful, inevitable flow. If classical physics, with its comforting predictability, treats time as a dependable train schedule, always on track, ticking along steadily, then quantum mechanics, with its captivating, sometimes bewildering nuances, treats it more like a jazz improvisation, flexible, mysterious, occasionally dissonant, and delightfully unpredictable. And just when you think you've grasped its rhythm, when you believe you understand what's truly going on, it throws you a metaphorical cat in a box, and asks you, with a knowing wink, to consider whether it's both perfectly alive and perfectly dead at the exact same moment. Welcome, dear listener, to the quantum world, where our everyday reality gets wonderfully fuzzy, and time often becomes more of a polite suggestion than an unbending, fixed rule. In the classical universe, the world of billiard balls and falling apples, you can generally point to an object and say, with confident certainty, it's right there, doing that precise thing, at this exact moment in time. There's a clear, discernible trajectory, a defined state. But in the enigmatic, shimmering quantum realm, the very nature of reality shifts. Particles, those fundamental building blocks of everything, don't have neat, well-defined positions or momentum simultaneously. Instead, they exist as ethereal probability waves, mathematical clouds of where they might be, what they might be doing, until observed. So, in this inherently uncertain landscape, where does time, our reliable guide, truly fit into all this? Surprisingly, time doesn't play the starring, dynamic role in standard quantum mechanics that it does in the grand narratives of classical physics or the sweeping elegance of general relativity. In fact, it mostly shows up as a quiet, unchanging background parameter. Something we simply plug into the equations to keep things gently moving. Like pressing play on a highly intricate cosmic simulation. Take, for instance, the famous Schrödinger equation, the foundational bedrock of non-relativistic quantum mechanics. It majestically describes how a quantum system's wave function, that peculiar, probabilistic cloud of possibilities, evolves over time. But unlike in general relativity, where time itself is dynamic, stretching, and bending, time in this foundational equation isn't something that bends, or stretches, or warps. It's just there, a silent, unblinking spectator. An external stopwatch that never changes, never warps, and certainly doesn't ask for any attention or special treatment. This creates a rather curious, profound split. On one hand, quantum mechanics brilliantly describes the evolution of states over time. But it doesn't, in itself, fundamentally explain what time is or where it comes from. It treats time as a fixed, absolute backdrop, much like Newton did. While all the vibrant, unpredictable dance of space and matter happens jiggling and uncertainly in front of it. But things, as you might expect in the quantum world, get even stranger, even more delightfully perplexing, when you introduce the ambitious concept of quantum gravity. This theoretical endeavor is the valiant attempt to merge the two colossal, seemingly incompatible titans of modern physics. Quantum mechanics, which governs the very small and the probabilistic, with general relativity, which governs the very large and the gravitational. These two theories, for all their individual brilliance, often don't get along well at theoretical parties. They speak different fundamental languages. In general relativity, as we gently discussed, space-time is wonderfully dynamic. It can stretch, curve, and evolve depending on the matter and energy within it. Meaning time is deeply interwoven into the fabric of the universe and is anything but absolute. But in quantum mechanics, as we just noted, time is fixed and unbending. A kind of cosmic metronome ticking reliably in the background. Trying to unify these two fundamentally different views of time is like trying to elegantly choreograph a classical ballet, using only the raw, powerful, and often chaotic instructions from a heavy metal concert. This profound conceptual clash leads us directly to what physicists reverently call the problem of time in quantum gravity. When you attempt to describe the entire universe, space, matter, energy, everything quantum mechanically, using the principles that govern the smallest scales, you often stumble upon something truly odd, truly mind-bending. Time, as we know it, seems to disappear from the fundamental equations. One of the most famous and unsettling equations that pops up in quantum gravity is the Wheeler-de Wit equation, which attempts to describe the quantum state of the entire universe. And the striking, almost chilling, feature of this equation is that it appears without any time variable. None at all. According to some interpretations of this equation, the universe, at its deepest quantum level, is fundamentally timeless. There's no past, no future, just an eternal present. A colossal, unchanging giant now. Imagine a cosmic photograph, fixed and unmoving, containing all possibilities at once. So, this brings us to a profound, almost whispered question. What, then, is truly going on? Is time real in the fundamental sense? Or is it just an elaborate illusion? A convincing narrative created by the very specific way we perceive and experience change. Some thoughtful physicists, leaning into the timeless implications of quantum gravity, believe that time is emergent, not a fundamental part of the universe's deepest reality. but something that appears only when you zoom out far enough. When you observe macroscopic systems, think of it like temperature. An individual molecule doesn't have a temperature. It has kinetic energy. But when you group trillions upon trillions of molecules together, their collective kinetic energy manifests as temperature, which emerges as a profoundly useful, descriptive property. In the same gentle way, time might emerge from the complex, statistical interactions of many quantum systems, a collective property rather than a fundamental dimension. Others look to the enigmatic phenomenon of entanglement, the bizarre quantum linkage where two or more particles become intimately connected, influencing each other instantly, regardless of the vast distances separating them. Some theoretical frameworks suggest that the arrow of time, that unidirectional flow, and perhaps even time itself, could arise from the inexorable growth of quantum entanglement throughout the universe. The more quantum-tangled the universe becomes, the more time seems to flow forward, creating a perceived directionality. And then, there's the wonderfully imaginative many-worlds interpretation of quantum mechanics, which offers a truly cinematic view of time. In this view, every single quantum event, every tiny, probabilistic choice made by a particle, every coin flip, every measurement, doesn't just resolve into one outcome. Instead, it causes the universe to literally branch into multiple, parallel realities. There's no true randomness in this perspective, just an infinite splitting of timelines. Time, in this fascinating view, isn't a simple, linear river. It's a vast, ever-branching tree. With every decision you make, every interaction, creating a new twig, a new alternate reality. Somewhere out there, there's a version of you who, perhaps, didn't forget their umbrella this morning, or who made that slightly different choice at a crossroads. But if time is such a shaky, uncertain concept at the fundamental quantum level, if it seems to vanish from the deepest equations, why then does it feel so profoundly solid, so undeniably real to us in our everyday lives? Well, we live in a world where countless quantum interactions average out into a smooth, reliable, and seemingly continuous classical reality. Our brains, those astonishingly complex organs made of trillions upon trillions of particles and intricate neural circuits, are hardwired, through eons of evolution, to perceive cause and effect, to impose a sequence on events. We wake up, brush our teeth, eat breakfast, and hopefully, smoothly, head to work, and almost always in that comfortable, predictable order. Time, for us, is a profound, comforting story, a necessary sequence of events that gives meaning to change, to growth, to memory, and to anticipation. And storytelling, as it turns out, is something humans are exceptionally good at. A fundamental way we make sense of our world. We string events together into coherent memories. We imagine possible futures, crafting plans and hopes. We define our very identities through time. Who we were in the past, who we are in the present, and who we aspire to be in what's next. Still, quantum mechanics, in its gentle, profound whisper, reminds us that underneath that comforting narrative, beneath that solid, ticking surface, lies something far more elusive, far more enigmatic. Time may not be the relentless ticking of a clock or the linear turning of a page. Instead, it might be the vast, continuous unfolding of possibilities, the graceful evolution of probability, the quiet, persistent hum of reality tuning itself, ever so slightly, with every passing moment, every quantum interaction. So, while your wristwatch gently, reliably says it's 10 minutes to midnight. Ready for a new day to begin. Quantum physics, with its playful, profound wisdom, quietly whispers, "Well, yes, darling, from a certain point of view, perhaps even from an infinite number of points of view, it invites us to ponder the deeper, more wondrous dimensions of existence, to embrace the beautiful, subtle uncertainties of the universe, and to find peace in the knowledge that even the most fundamental concepts can hold layers of mystery, waiting to be gently explored." Time, in its vast and multifaceted forms, isn't just something tracked by the precise ticking of atomic clocks, or the majestic, predictable orbits of planets around a star. Number, it's also humming quietly, persistently, intimately inside you, deep within your very cells, influencing your sleep, your appetite, your mood, and even the subtle shifts in your body temperature throughout the day. Whether you identify as a vibrant night owl, an energetic early bird, or perhaps a perpetually groggy, endearing pigeon, your entire biological system is running on its own intricate, ancient internal clock. And it's a very, very old one indeed. A rhythm woven into the very fabric of life. This internal clock, or more precisely, a wondrous, interconnected network of them, residing within nearly every cell of your body, is what scientists reverently call the circadian rhythm. The term itself comes from the Latin phrase circa diem, gently meaning about a day, perfectly capturing its essence. Circadian rhythms are the remarkable biological processes that faithfully follow a roughly 24-hour cycle, orchestrating a vast symphony of physiological functions. They meticulously regulate everything, from when you feel a gentle wave of sleepiness begin to wash over you, to how your body efficiently processes the food you eat, to the precise timing of hormone release. And what's truly remarkable is that they're found in nearly all living things. Humans, of course, but also the towering trees, the smallest insects, the deep-sea creatures, the tiny fungi that carpet the forest floor, and even some of the most ancient, unassuming bacteria. If it's alive and vaguely organized, it probably, quietly, tells time in its own biological way. The master conductor of your personal circadian orchestra, the tiny, brilliant maestro, is a minuscule region nestled deep within your brain, elegantly named the suprachiasmatic nucleus, or SCN for short. It's located in the hypothalamus, a vital command center, just above the point where the optic nerves, the pathways from your eyes, cross. This positioning is not accidental. It's a very strategic, brilliant design, because it allows your master body clock to sync up almost instantaneously and profoundly with the most powerful external time cue, light. When your eyes detect the golden glow of morning sunlight, or even the soft illumination of artificial light, the SCN receives the memo with remarkable speed and precision. It then sends out a cascade of intricate signals to adjust everything, from your hormone levels, like cortisol, which promotes alertness, to your core body temperature, which fluctuates throughout the day. It's like your brain's sophisticated, internal version of tapping the snooze button on the sun, gently resetting your day each morning. One of the SCN's most crucial and well-known jobs is controlling the precise release of melatonin, often affectionately called the sleep hormone. Melatonin levels naturally begin to rise in your body as evening gently descends, sending a calming signal to your brain that it's time to feel drowsy and prepare for rest. Conversely, these levels naturally fall in the morning, helping you feel refreshed and ready to wake up. It's your body's ancient, subtle way of saying, "Hey, maybe don't watch another episode right now, sweet one. It's getting late. Whether or not you listen to this gentle, biological advice is, of course, another matter entirely, often determined by the irresistible pull of just one more chapter. But here's the truly fascinating thing. While your circadian rhythm runs on a roughly 24-hour cycle, it's not exactly 24 hours. Most humans naturally run a tiny bit long, clocking in at about 2 hours. Give or take a few minutes. A subtle, intrinsic drift. This means that if we were left entirely to our own devices, perhaps in a quiet, lightless cave with no clocks, no external cues, we'd gradually, subtly drift out of sync with the actual solar day, extending our internal day a little bit each time. Light exposure, particularly the vibrant, full-spectrum light of morning sunlight, is what acts as our anchoring force, our cosmic reset button. Morning sunlight resets the SCN clock daily, keeping us in beautiful harmony with the Earth's rotation, or at least vaguely, delightfully within range of our morning alarms, preventing us from perpetually living a slightly longer day. Disrupt this delicate, exquisitely tuned biological system, and things can get wonderfully, sometimes uncomfortably, weird. Enter jet lag, humanity's least favorite travel souvenir. A testament to the power of our internal clocks. Jet lag happens when your internal clock is dramatically out of sync with your new external environment. Say, when you fly across several time zones in just a few hours. Suddenly, your brain, convinced it's midnight, is trying to tell your body it's time for deep sleep, when it's actually lunchtime in your new location. And your stomach, your liver, your immune system, and a myriad of other cellular processes are all deeply, delightfully confused, each trying to adjust at its own unique pace. That's because different parts of your body, different peripheral clocks in your organs, adjust to new time zones at different speeds. Your SCN, the master clock, might reset relatively quickly, especially with bright light exposure. But your digestive system, your liver, or even your muscle cells might still be living in last week's time zone, wondering why dinner smells suspiciously like airport pretzels at what feels like 3 a.m. Another modern culprit that subtly, yet profoundly, impacts our biological time, is the pervasive presence of artificial light. Before the widespread advent of electric lighting, humans were largely, and beautifully, guided by the natural rhythm of daylight. We woke up with the gentle caress of the sun's first rays, and naturally felt sleepy as it set, a fundamental rhythm still wonderfully preserved in traditional societies with minimal exposure to artificial light. But today, we're constantly surrounded by screens, tablets, and LED bulbs that emit significant amounts of blue light, particularly in the evenings. This blue light, with its stimulating wavelengths, tricks our SCN into thinking it's still broad daylight, even when it's late at night. This can powerfully suppress melatonin production, pushing our circadian rhythm later and later, making it significantly harder to fall asleep when we want to, and more difficult to wake up feeling truly refreshed. It's not so much that we've suddenly become night owls as a species. It's more like we've inadvertently invited a glowing, persistent neon owl into our living rooms, and, with a sleepy sigh, handed it the remote control to our internal clocks. Interestingly, not everyone's circadian rhythm operates on the exact same internal schedule. Some people are naturally morning types or larks, who spring out of bed with suspicious amounts of energy and cheerful alertness, ready to tackle the day at dawn. Others are instinctively evening types or owls, who find their creative stride and peak alertness just as everyone else is winding down for the night, perhaps brushing their teeth for bed. These unique chronotypes are partly, fascinatingly, genetic. So, if you're genuinely not a morning person, if the early hours feel like a foggy, unconquerable frontier, it's probably not just laziness. Your brain genuinely, biologically doesn't believe it should be awake yet, still preferring the quiet lull of deeper sleep. And honestly, who are we, with our fleeting modern schedules, to argue with a billion years of deep, evolutionary wisdom? Circadian rhythms also subtly, yet powerfully, influence our core body temperature, which typically drops to its lowest point in the early morning hours, usually during deep sleep, and then gradually rises throughout the day, peaking in the late afternoon or early evening. This natural fluctuation is part of why many athletes and performers tend to do better later in the day. When their bodies are warmer, their reflexes are sharper, and their alertness is at peak efficiency. On the flip side, this is also why early morning presentations or demanding tasks can sometimes feel like trying to do complex calculus while half frozen. Your brain and body still gently thawing into full functionality. But the influence of biological time, this quiet, internal drumbeat, goes far beyond mere sleepiness and thermal regulation. It affects your metabolism, guiding when your body is best at processing nutrients. It modulates your immune system, influencing your body's ability to fight off illness. It plays a role in your mood, impacting levels of alertness and energy throughout the day. And perhaps most surprisingly, it even affects how you respond to medications. There's a growing, fascinating field called chronopharmacology, the study of how drug effectiveness changes depending on the time of day they are administered. It turns out that timing really, truly matters. The same medicine might work far better, with fewer side effects, when taken in the morning or the evening, depending on what it targets and your body's biological readiness to absorb and utilize it. Plants too, those silent, rooted observers of time, beautifully follow circadian rhythms. They gracefully open their leaves to the sunlight during the day, maximizing photosynthesis, and gently close them at night, conserving energy. They even anticipate dawn, starting to subtly stir unprepareful light, slightly before the first rays hit, a testament to their internal clock. This isn't just a passive response to light. It's an active, internally driven cycle that persists even if the plant is kept in constant darkness, gently proving its intrinsic nature. The sunflower doesn't follow the sun because it sees it moment by moment. It turns and tracks its path because it remembers its journey through the internal rhythm of its cells. And in the vast, diverse world of animals, from the majestic migratory birds that cross continents, to the busy, industrious bees navigating their hives, to the nocturnal rodents scuttling in the dark, circadian rhythms help regulate everything from migration patterns to foraging behaviors to the deep, extended slumber of hibernation. Even fungi, those mysterious, often overlooked dwellers of the forest floor, possess intricate internal clocks that govern their spore release and growth cycles. All of this, dear listener, paints a profound, beautiful picture of life on Earth, as deeply, intimately intertwined with time. Not the abstract, cold kind measured by atomic clocks in distant labs, but a warm, living, biological time, profoundly grounded in the ancient, rhythmic dance of light and dark, warmth and cold, hunger and rest. A time that pulses, gently and reliably, through every living thing, like a shared, invisible drumbeat echoing through the eons. So, The next time you feel a wave of fatigue at 3 p.m. or find yourself unusually, creatively perky late at night, remember, it's not random. It's rhythm. Your body, your very cells, are gracefully dancing to an ancient, invisible beat. A cosmic symphony that kept our ancestors safe, healthy, and well rested. Long before the complexities of time zones, the convenience of digital watches, or the stimulating jolt of a double-shot espresso. And while we may try, with our modern schedules and artificial lights, to bend time to our will, deep down, our cells are still following the sun. Slowly, quietly, faithfully, in that profound, ancient dance. Have you ever truly, deeply noticed how time seems to play favorites? How it stretches and compresses with such whimsical, delightful inconsistency? A cherished holiday week, brimming with laughter, new sights, and warm connections, often flies by like a feather caught on a gentle breeze, leaving us with a wistful sigh and a lingering sense of its brevity. But then, there's the agonizingly slow crawl of the last 10 minutes of a Zoom call you never really wanted to be on in the first place. That, dear listener, can feel like you're not merely trapped, but gently, endlessly simmering in a slow-cooking rice pudding of eternity. This isn't just poetic exaggeration, a trick of language. There is, indeed, a profound reality at work here, psychological time. That is the wonderfully warped, deeply personal way our minds perceive time's passage, which, as we've seen, often has very little to do with the objective, unwavering tick of clocks and calendars. If physics, with its grand equations, valiantly tries to describe time as it is, in its pure, objective form, then psychology, with its delicate insights, beautifully tries to explain how it feels. And those two perceptions, as we'll gently explore, can be wildly, beautifully different things. Let's begin with perhaps the most universally recognized, yet often unexamined, distortion of psychological time. Time flies when you're having fun. This beloved cliché actually holds up remarkably well to rigorous scientific scrutiny. A comforting validation of our lived experience. When we are deeply, utterly engaged in an activity, whether it's losing ourselves in a captivating conversation with cherished friends, immersed in a beloved hobby that lights up our soul, or watching something genuinely riveting, perhaps even a sleepy scientist gently unraveling the mysteries of the cosmos, we are, by definition, not paying close, conscious attention to time itself. Our focus, our entire mental energy, is completely absorbed in the vibrant, unfolding moment, in the richness of the experience. And when our attention is so profoundly absorbed, our brain effectively stops its diligent, meticulous counting of the seconds. Its internal stopwatch falls silent. The beautiful result: time simply appears to vanish, leaving only the lingering echo of joy and engagement. On the flip side, we encounter the equally potent, often unwelcome, truth that boredom stretches time like taffy. When nothing in our immediate environment, or within our internal landscape, is truly engaging us. When our minds are starved for meaningful stimulation. Say, you're patiently waiting at the DMV, watching paint dry with an almost meditative intensity, or enduring someone explaining cryptocurrency for the 15th time with undiminished enthusiasm. Your brain, seeking something to occupy its processing power, inevitably starts clock-watching. It becomes hyper-aware of each passing second. Each moment feels languidly, interminably longer than it actually is. The watch pot, indeed, refuses to boil. And time, in its cruel, drawn-out way, seems to solidify. Each tick an eternity. There's also the peculiar, fascinating phenomenon of retrospective versus prospective time. How we perceive time while we're living it versus how we remember it later. When you're in the moment, time might feel delightfully fast or agonizingly slow, depending on your engagement level. But when you cast your mind back on it, when you retrospectively evaluate it, the effect can curiously reverse. Let's imagine you spent a week hiking through unfamiliar, breathtaking terrain, encountering new challenges and stunning vistas each day. During that week, the days might have felt like they flew by, each moment a thrilling blur of activity. But looking back on it later, the trip feels surprisingly long, packed with a rich tapestry of vivid memories and distinct experiences. That's because novel, new experiences create far more mental bookmarks or memory markers. Your brain, in its diligent wisdom, stores more detail, more unique moments. And that abundance of stored information gives the powerful impression that more time has passed. Contrast that with a week where you faithfully followed the same comfortable routine every day. Wake, work, Netflix, sleep. While you lived it, it might have felt agonizingly slow, a monotonous march. But in hindsight, it blurs together into a compressed, indistinguishable block. Fewer new experiences, fewer memory markers, and consequently, less perceived time. This fascinating interplay between novelty, memory, and perception is a significant part of why time seems to speed up, a gentle, accelerated blur, as we gracefully get older. When you're young, everything, almost literally everything, is new. Your brain is a sponge, constantly learning, recording, and marking the moments with unparalleled intensity. Your first bike ride, the first prickle of heartbreak, your first wonderfully awkward haircut. All these moments are logged in crisp, vivid detail, each a unique, indelible bookmark. As we age, however, we tend to settle into more familiar, comfortable routines. There are fewer grand surprises, fewer entirely novel experiences, and consequently, fewer distinct memory markers. Days blend into each other, weeks become a seamless flow, and suddenly, entire decades seem to have passed in a blink. A soft, accelerated whoosh. It's not that time itself is objectively going faster. It's that our brains are logging it less actively, less granularly. We're no longer wandering new, exciting trails, but building mental highways, efficient and smooth, but with less to distinguish one mile from the next. There's also the curious, profound effect of emotional intensity on our perception of time. When we're gripped by strong emotions, particularly fear or intense anxiety, time often feels like it slows down. Moments elongating into what feels like a vast, stretched out eternity. This isn't just dramatic storytelling in movies. It's a phenomenon that has been rigorously tested in laboratories. People who experience sudden, intense shocks, like bungee jumps or simulated freefalls, often report a feeling of stretched out moments, as if time itself has become syrupy. One leading theory is that the brain, under extreme stress, goes into cognitive overdrive, dramatically increasing its processing speed and capturing far more detailed information per second than usual. Later, when we recall that event, the incredibly dense, rich memory gives the powerful illusion of slow-motion playback, a vivid, almost hyperreal recollection. But interestingly, and this is a key distinction, time doesn't actually slow down in the moment itself. In experiments, people don't perform actions faster or process information more quickly during the event. They just remember it as having been longer afterwards. So, while your memory might whisper, "That was the longest roller coaster drop of my entire life," your trusty stopwatch, if you had one, would calmly say. Actually, it was a perfectly normal 3.2 seconds. Still impressive, to be sure, just not a Matrix-level distortion. Then there's attention, perhaps the most potent and subtle shaper of psychological time. When we pay close, meticulous attention to time itself. Like patiently waiting for a batch of warm, fragrant cookies to bake. Or watching the seconds tick by on an exam. We experience every single tick of the clock. Each moment stretched by our focus. But when our attention is elsewhere, fully absorbed in a beloved piece of music, deep in the pages of a captivating book, or utterly lost in a rich, flowing conversation, time gracefully recedes into the background, becoming an almost unnoticed hum. This profound observation ties very closely to practices like mindfulness and meditation, which deliberately train us to shift our attention away from time, away from the past and future, and firmly into the vivid, unfolding present moment. When we focus on a single breath, a gentle sound, a fleeting sensation, time seems to dissolve, to lose its grip. It's not that we enter a trance or lose touch with reality. It's that we simply stop measuring time, and instead, quietly, profoundly exist within it. For many, this feels deeply, wonderfully freeing. You're no longer anxiously chasing the next hour, or regretting the last. You're simply living fully, richly, and meaningfully in this one. On the more complex and intriguing end of the spectrum, there are altered states of consciousness. These states, sometimes brought on by deep, sustained meditation, intense emotional experiences, or certain mind-altering substances, are where people report truly radical distortions of time. Time slowing to an almost standstill, speeding up to a blur, looping back on itself, or even disappearing entirely. Some individuals describe moments of timelessness, not a mere distortion of time, but the profound, almost spiritual absence of it, as if for a brief, transcendent moment, they stepped entirely outside the river of time, and looked at it, serene and detached, from the quiet bank. Neurologically, these extraordinary experiences may involve significant changes in activity within the default mode network of the brain. A fascinating set of interconnected regions involved in self-referential thought, remembering the past, imagining the future, and processing our normal sense of time. When this network, which is usually highly active, quiets down or its connectivity shifts, our conventional sense of identity, and, crucially, our normal linear perception of time can temporarily dissolve, leading to those profound feelings of timelessness or unity. This might beautifully explain why your most timeless moments, moments of flow, deep stillness, or profound connection, often feel the most meaningful, the most sacred, untethered from the relentless march of the clock. Children, though small, bright beacons of pure experience, too, have their own wonderfully unique relationship with time. For very young kids, time is often fluid, delightfully imprecise, and mostly irrelevant to their immediate, vibrant play. Ask a 5-year-old how long 5 minutes is, and you'll likely get an answer that delightfully involves forever, if they're waiting for something fun. Or until I finish this snack, if they're fully absorbed. Only as they grow older, as they are gradually introduced to the rigid demands of clocks, the structure of schedules, and the dreaded, endlessly repeated phrase, just a few more minutes, do they begin to reluctantly align their inner rhythms with adult, conventional time. Some might argue, with a wistful smile, that this slow, inevitable alignment is, in its own way, the true, gentle loss of innocence. And finally, there's anticipation. Our brain's remarkably sophisticated, built-in time machine, looking forward to something joyful and highly anticipated. A long-awaited vacation, a special gathering, a beloved concert, often makes time feel like it slows down to an agonizing crawl. Each day leading up to the event is stretched, magnified by our longing. Conversely, dreading something unwelcome can do the exact same thing, making the approaching moment feel interminable. We meticulously imagine future events in vivid detail. We rehearse conversations, we worrying over countless possible outcomes, all using the same intricate neural machinery we employ to recall the past. Time, in this profound sense, becomes wonderfully elastic, stretched and shaped by the powerful forces of hope and fear alike. So, is psychological time reliable, a precise instrument mirroring the universe? Not really, no. Is it always logical, following clear, predictable rules? Often no. It delights in its own internal contradictions. But is it deeply, wonderfully human? Absolutely, yes. We may live in a universe governed by the objective ticking of atoms and the majestic, predictable orbits of planets. But the time we actually experience, the time that profoundly colors our lives, is a vibrant, intricate tapestry woven from our fleeting memories, our swirling emotions, the shifting focus of our attention, and the boundless realm of our imagination. It's time felt, time lived, not merely time measured. And maybe, just maybe, that's precisely why it feels so intensely personal, so beautifully strange, and so delightfully, charmingly inconsistent. It is, after all, the time of our lives. Let's be honest, dear listener. No profound discussion of time is truly, completely satisfying until we bravely, perhaps a little dreamily, ask the question that has launched 1,000 thrilling sci-fi novels, inspired countless mind-bending thought experiments, and, let's admit, enthusiastically derailed more than a few perfectly good dinner party conversations. Can we travel through time? Well, the answer, as with many of life's most intriguing mysteries, is complicated, nuanced, and delightfully speculative. Time travel, at least in its theoretical permutations, isn't entirely, absolutely forbidden by the elegant laws of physics. In fact, according to the visionary insights of Albert Einstein's general relativity, the very fabric of spacetime, that interwoven tapestry of space and time, is not rigid and unyielding, it's wonderfully flexible, a dynamic entity that can stretch, warp, and under the right, incredibly extreme, and possibly highly impractical, circumstances, even loop back on itself, creating pathways that might, just might, lead back to an earlier moment. If that profound, mind-bending possibility is true, then the idea of gracefully zipping to the past or effortlessly leaping into the far future isn't completely out of the question. It's merely a matter of immense engineering and cosmic conditions. Let's start with the easy kind of time travel, the gentle, relatively straightforward leap into the future. This one's not just theoretically possible. It's already been subtly, undeniably done. Remember our earlier, delightful discussion of asterisk time dilation, asterisk from special relativity. If you move very, very fast, accelerating to speeds incredibly close to the speed of light, time, for you, quite literally slows down relative to someone standing still or moving at a much slower pace. Imagine, for a moment, that you were to board a state-of-the-art spaceship and zoom off at near light speed for a grand cosmic adventure, perhaps to explore a distant star system. When you eventually return to Earth, decades, perhaps even centuries, could have passed here, while you'd only aged a few years, or even mere months. Subjectively, congratulations, you've time-traveled into the future. No complicated flux capacitor or blue police box required. Just a very, very fast ride. This phenomenon isn't confined to theoretical thought experiments or distant galaxies. It's been observed and precisely measured in our own cosmic neighborhood. Astronauts who spend months aboard the International Space Station (ISS), though not traveling at near light speeds, are still moving considerably faster than us on Earth, and are also in a slightly weaker gravitational field. They experience a tiny, but measurable, bit of time dilation when they return to Earth. Their clocks, and indeed their biological aging, are ever so slightly behind those who remained on the planet. They return to Earth a few microseconds or milliseconds in the future, technically still perfectly on time for lunch, though perhaps with a newfound appreciation for the passage of ordinary moments. So, future time travel. Check. Done. Relatively easy, if you have a rocket. But now, for the real mind-bender, the tantalizing, deeply complex question. What about gracefully traveling into the past ? Here, dear listener, things get considerably trickier. Entangled in fascinating theoretical knots and perplexing paradoxes, general relativity, in its remarkable mathematical elegance, does allow for certain solutions to its equations that could, in theory, permit backward time travel. These include exotic, hypothetical phenomena like closed time-like curves CTCs, which are essentially loops in spacetime where an object, if it follows such a path, could return to an earlier point in its own history, revisiting its own past. Think of it like walking a grand, intricate lap around a universe and magically ending up back at yesterday's breakfast table. One popular theoretical proposal for actualizing such a journey involves something called a wormhole a hypothetical, fascinating tunnel connecting to distant points in spacetime, like a shortcut through the cosmic fabric. The idea is that if one end of this wormhole was somehow accelerated to near light speed, then brought back to its original location, time at that end would, due to relativistic effects, lag significantly behind the other end. Step through the accelerated end of the wormhole, and boom, you've theoretically arrived in the past. The practical problems with wormholes, however, are, well, monumental, almost comically so. First, we're not even sure they exist outside of mathematical theory. Second, if they do, they may be incredibly unstable, collapsing instantly the moment anything tries to pass through them. And third, keeping one open and stable would require something utterly exotic and currently purely theoretical called negative energy or exotic matter, something emphatically not currently available in your average home improvement store, or indeed, anywhere we know of. So, while wormholes are exquisitely fascinating on paper, building one might be slightly, just slightly, beyond our current engineering abilities, give or take a few millennia. But even if, by some miracle, we could construct such a pathway back in time, we would immediately, and quite uncomfortably, run into some rather sticky, logic-defying paradoxes. The most famous and conceptually troubling is the grandfather paradox Imagine, you bravely, or perhaps carelessly, travel back in time, and, through some unfortunate turn of events, prevent your own grandfather from meeting your grandmother. Consequently, your own parents would never be born, and thus, you yourself would never come into existence. But if you were never born, how did you go back in time to begin with? It's a loop that logic simply can't quite untangle. A cosmic contradiction that ties the very fabric of reality into an impossible knot. There are, however, a few ingenious ways scientists and philosophers have tried to make sense of this, to gently untangle the knot of the grandfather paradox. One elegant idea is the block universe model which we'll discuss more deeply in our next chapter. In this view, all moments in time past, present, and future exist simultaneously, like fixed frames in a long, eternal film reel. In this perspective, the timeline is unchangeable, immutable. If you go back in time, everything you do, every action you take, was always, in a profound sense, already part of the past. So, you can't actually change anything. You're simply playing your preordained role in an already written scene, an actor fulfilling a script. This neatly avoids the paradox by eliminating the possibility of altering the past. Another fascinating possibility, one borrowed from the intriguing realm of quantum mechanics, is the many worlds interpretation *. In this scenario, if you go back in time and change something, you don't alter your original timeline. Instead, your action causes the universe to branch into a new, parallel universe, where events unfold differently. You can indeed stop your grandfather from meeting your grandmother, but it only affects that newly created branch of reality. Your original self, the one who initiated the time travel, is still safely anchored in their own universe, perfectly free from paradoxes and awkward, non-existent family dinners. Then there's the delightfully cheeky and very scientifically sounding Novikov self-consistency principle proposed by Russian astrophysicist Igor Novikov. This principle essentially says that you simply can't create a paradox, no matter how hard you try, because the universe itself has a built-in protection mechanism. If you go back in time, the cosmos will somehow, perhaps subtly, prevent you from doing anything that would change the future in a paradoxical way. Try to assassinate your grandfather. Your gun will jam, or you'll trip and fall, or he'll unexpectedly join a monastery just before you arrive, or a sudden, unexpected meteor will fall precisely between you and him. It's like the universe has an omniscient, cosmic insurance policy against timeline tampering, ensuring consistency. Still, all of this, dear listener, remains deeply theoretical and highly speculative, a delightful playground for the imagination, rather than a blueprint for a future invention. No one, to our current knowledge, has ever successfully built a functional time machine. No one has ever definitively documented a real, undeniable time traveler, not for lack of intriguing claims, as the internet is delightfully full of interviews with suspiciously modern-looking figures in old photographs, or blurry videos of alleged temporal tourists, and physicists still vigorously debate whether the intricate mathematical framework, general relativity, truly permits or fundamentally prohibits time loops and backward travel. One particularly interesting point of contemplation arises if backward time travel were, in fact, possible, and if someone in the distant future eventually invents such a device, where, then, are all the time tourists? Shouldn't we, by now, be knee-deep in curious visitors from the year 4000, perhaps taking selfies with dinosaurs in ancient forests, trying to subtly blend in at medieval banquets, or offering unsolicited stock tips to historical figures? Some theories suggest that time travel might be fundamentally limited to the point of its own invention, meaning you can't go back to before the very first time machine was created, placing a theoretical chronological protection conjecture. Others think time travelers might be incredibly discreet, observing from the shadows, or perhaps, and this is the most realistic thought, time travel into the past is simply impossible, despite what the tantalizing equations occasionally tease us with. And maybe, just maybe, that's truly for the best, as much as we fantasize, in our quiet moments, about revisiting the past to fix old mistakes, to relive cherished moments, or to buy absurd amounts of Bitcoin, before it surged. Perhaps, time's inherent, one-way nature is precisely part of what makes it so profoundly meaningful. We can't simply edit our lives like a video, jump back to a scene and reshoot it. We must move forward, moment by precious moment, with all the richness, the beautiful imperfection, and the thrilling unpredictability that comes with it. Still, It's undeniably fun to dream, to let our minds wander into these cosmic possibilities, isn't it? And who knows? Maybe someone from a far future is listening to this right now, nodding quietly, and thinking, oh, yes, the primitive, charming beginnings of temporal theory. How quaint. If so, welcome, dear temporal traveler, and please, for the sake of our serene slumber, don't spoil how this chapter, or indeed, the grand story of time, ultimately ends. Let the mystery gently unfold. After our long, winding, and wonderfully contemplative journey through the vast, intricate landscapes of time, from the ancient, sun-drenched dials and the rhythmic flow of water clocks, to the breathtaking precision of atomic clocks, after riding the warping waves of Einstein's spacetime, puzzling over the mind-bending paradoxes of time travel, and daring to stare down the perplexing question of whether the future is already written, we arrive, at last, at perhaps the strangest, most profound question of all, a question so fundamental, so deeply unsettling in its implications, that it often feels like the kind of thing you'd only hear at 2 a.m. in a dimly lit dorm room, filled with empty tea mugs, crumpled notes, and earnest, perhaps slightly wild, eyebrows. The question, does time actually exist? Now, that might sound, at first whisper, like a philosopher's trick, a delightful intellectual game designed to tease and provoke, but it's a question that physicists, especially those delving into the deepest, most fundamental theories of the universe, also take profoundly, unsettlingly seriously, because when you gently peel back the layers of how we experience time, and how we attempt to describe it mathematically within our most advanced physical theories, something truly strange and disquieting starts to happen. Time, as we conventionally understand it, begins, curiously, to disappear. Let's begin our final reflection with a gentle reminder of how most of us intuitively think of time. For the vast majority of us, it feels like an immense, silent river, flowing smoothly, relentlessly, carrying us, like tiny leaves, from the indelible past, through the fleeting present, and onward into the mysterious future. We're all floating downstream, unable to paddle backward against the current, able only to move forward, sometimes gently, sometimes caught in a rush, but always forward. This deeply ingrained, intuitive understanding is what philosophers call presentism, the profound idea that only the present moment, this now, is truly real. The past, in this view, is gone, irrevocably vanished, existing only in our memories. The future doesn't exist yet. It's an unwritten script, a realm of pure potential, and now is all there ever truly is, a constant, fleeting point of existence. It aligns perfectly, beautifully, with how we live our lives, moment by moment, breath by breath, ticking along in comforting synchronicity with our clocks and calendars. But then, there's another, profoundly counterintuitive idea, one that Einstein's groundbreaking theories of relativity, both special and general, helped to make famous, or perhaps infamous, for their mind-bending implications. It's called eternalism, sometimes referred to as the block universe theory, and in this view, time doesn't flow at all, not in the way a river does. Instead, all moments in time, past, present, and future already exist, laid out in their entirety. Simultaneously, the universe, in this radical perspective, is like a fixed, four-dimensional block, a massive, unchanging cosmic entity. Time isn't something we move through rather, it's a dimension we are inherently part of just like the spatial dimensions of length, width, and height. In this view, your childhood, your current self, your future retirement, and every single moment in between are all laid out, fixed and unchangeable, like distinct pages in an infinitely long book. You don't become older. You already are older on some distant page of the cosmic book, and younger on another. You're not surfing time. You're a static thread woven into the intricate, eternal fabric of a space-time quilt, comforting in its completeness. Maybe, in a strange, cosmic way, a little spooky in its determinism. Also, undeniably, yes. This eternalist concept arises naturally, almost inevitably, from relativity. Remember how simultaneity, the idea that two events happen at the same time, depends entirely on your motion, on your frame of reference. Two observers moving at different speeds can profoundly disagree about what now means, about which events are happening right now. That suggests there's no single, universal present moment, no cosmic stopwatch ticking universally and equally for everyone, which makes the whole intuitive idea of a moving present a bit wobbly, a rather local illusion. If that's not enough existential spice to gently stir your thoughts, the realm of quantum gravity adds another, even more disquieting twist. We touched on this in our quantum mechanics chapter. Remember, when you try to combine the principles of quantum physics, which govern the very, very small, with general relativity, which describes gravity and the large-scale structure of spacetime, something truly unsettling frequently happens in the resulting equations. Time often simply drops out of them altogether. In the famous Wheeler-DeWitt equation, for example, an ambitious attempt to describe the quantum state of the entire universe, there's explicitly no time variable none. The universe, according to some interpretations of this equation, is fundamentally timeless. There's no inherent past, no future, just a colossal, unchanging giant now, an eternal cosmic snapshot containing all possibilities simultaneously. So, what are we to make of this profound, mathematical disappearance? If time doesn't exist at the deepest, most fundamental level of reality, why then does it feel so undeniably, compellingly real to us? One possible, and rather elegant, answer is emergence. Time, like temperature or sound, may not be a fundamental ingredient of the universe, a primary building block. Instead, it might arise from more basic, underlying relationships between things, from patterns of change, from interactions, from the way information flows and diffuses. This is similar to how we perceive motion in a film. A movie is just a rapid sequence of still frames, static images shown one after another. But when these still frames are shown rapidly enough, our minds, in their ingenious way, perceive continuous, flowing motion, a cohesive narrative. Some physicists suggest that time might work in a remarkably similar way. What we perceive as the ceaseless passage of time is really our brain stitching together, interpreting, and ordering changes in a fundamentally timeless, static reality. Enter the brilliant, iconoclastic physicist Julian Barber, who goes even further with this idea. In his radical, thought-provoking view, time doesn't exist at all, not even as a background parameter. Instead, the universe, at its most fundamental level, is a vast, unchanging landscape of nows, complete, timeless snapshots of the universe, each existing independently. These nows don't change or evolve. They just exist eternally. Our experience of time, he argues, comes from the way these nows are structured, how memories are embedded within them, creating a sense of sequence. It's like a colossal, cosmic photo album, if you like, with our consciousness, our perception, simply flipping through the static pages, creating the illusion of movement and flow. It's a truly radical idea, one that challenges our deepest intuitions. But it raises an interesting, profound possibility. Maybe the sensation of time passing is a feature of our perception, a product of our consciousness, not a fundamental property of physics itself. After all, we humans are, by our very nature, narrative creatures. We are hardwired to remember the past, to anticipate the future, to tell stories about our lives and the world around us. We measure time because it helps us organize our experiences, plan our days, coordinate our actions, and understand change, growth, and decay. Time is undeniably useful, perhaps even essential, for sentient beings navigating a dynamic, ever-changing world. But that doesn't necessarily mean it's real in the same way a solid rock is real, or a distant star is real, or even a delicious slice of cake is real, which, mysteriously, also disappears with the passage of time. Still, not everyone agrees that time is ultimately an illusion or merely emergent. Many thoughtful physicists argue that even if time emerges from more fundamental processes, or if it's merely a useful parameter, it still has very real, undeniable effects that shape our reality. Clocks tick, planets orbit, radioactive elements decay. Cause leads to effect. If we build a machine that consistently measures change, and that machine agrees with all the other machines, and its measurements allow us to make remarkably accurate predictions about the universe, doesn't that, in a profound and practical sense, make time real enough? Maybe that's the best, most comforting answer we can find. Time is real in the same way stories are real, not because you can hold it in your hand or isolate it in a test tube, but because it structures the way things happen, gives meaning to events, and shapes our understanding of existence. It's the profound, invisible script that allows events to make sense, to follow a coherent narrative, even if the script itself is printed on quantum paper that's written in a language we don't yet fully, truly understand. So, as the quiet of the night deepens, and your thoughts begin to gently drift, does time exist? Well, perhaps not in the simple, absolute, flowing way we often instinctively think it does. It might not be a distinct flowing thing or a ticking clock hidden behind the scenes, but it exists, profoundly, undeniably, in our personal experience, in the intricate rhythms of our biology, in the shared tapestry of our culture, and in the elegant language of our equations. It exists in how we live each precious moment and how we lovingly remember the past. It exists in every single heartbeat, every gentle breath, and every comforting bedtime story we tell or hear. And maybe, just maybe, that's enough, because whether time is fundamental or emergent, real or imagined, absolute or relative, it undeniably gives shape, rhythm, and profound meaning to our lives. It reminds us, with gentle persistence, that everything changes, that moments are fleeting and precious, and that somewhere, woven into the very fabric of the universe, you, dear listener, are quite exquisitely timeless here. And so, dear listener, as the quiet of the night deepens, and your own internal clocks begin to slow, we gently arrive at the end of our little voyage. Or perhaps, more poetically, we've simply come to another precious, unique moment in the vast, looping, ever-unfolding sea of them, a moment to pause and reflect before the next gentle current carries us along. We've wandered together through the grand, ancient sundials that stretch towards the sky, charting shadows and seasons, and marveled at the almost unfathomable precision of modern atomic clocks, which hum with the very vibrations of reality. We've ridden the subtly warping waves of Einstein's spacetime, feeling how speed and gravity can gently stretch and compress the moments we live. We've puzzled, with a shared sense of wonder, over the mind-bending paradoxes of time travel, debating the fate of paradoxes and the whispers of other branching universes. And we've dared, finally, to stare down the ultimate, most profound question: Does time, in its deepest, most fundamental essence, even exist at all? Along this winding path, this gentle expedition, we've seen that time is not just one simple, monolithic thing, but a beautiful, intricate tapestry woven from many threads. It's a rhythm felt deep in the quiet hum of our biology, a clever trick played by the whimsical nature of memory and the shifting focus of our attention, a subtle wrinkle in the grand fabric of gravity, and a comforting story gracefully told by the ceaseless dance of change itself. And now, here you are, a little farther along your own unique timeline than when we gently began this conversation. But was it merely seconds, or perhaps many tranquil minutes? Or did the flow of words, the unfolding of ideas, stretch and shrink in your mind, just like it so often does when your thoughts begin to soften and your consciousness gently prepares for the embrace of sleep? So let me ask you once more, softly, with no expectation, just a gentle invitation, as I did at the very start of our journey. Where in the world are you listening from tonight, in this quiet, precious moment? And what time, in its beautifully relative way, is it right now in your little corner of the world? Funny, isn't it, after all this talk about time being relative, flexible, an illusion, perhaps even disappearing at the quantum level, we still instinctively, beautifully anchor ourselves to it. A glowing number on a digital screen, the hushed quiet of late evening, the feeling of winding down, breath by soft breath, as the day releases its hold. And if you found any calm in this quiet expedition, if the wonders of the cosmos, gently unfurled, gave you peace, or if the profound questions helped you drift gently, serenely into your dreams, I'd be ever so grateful. A gentle like on the video, perhaps, or a soft click to subscribe, and maybe, just maybe, sharing this sleepy space with someone else who might also need a peaceful pause, a moment of gentle scientific wonder, before they to find their way to rest. Time may be slippery, strange, and possibly, in its deepest essence, a complete illusion. But right now, here in this very moment, as the world settles into slumber, it's just you, this quiet voice, and the slow, soothing rhythm of rest. Let that rhythm carry you gently now. Sleep well, fellow traveler, wherever and whenever you are in the grand, timeless dance of the universe. May your dreams be peaceful and your rest profound. Good night.